Are we recording? Okay, great. So we'll go to review of linear equations. This is something that you're more familiar with than what we did in the last lecture, but I'll still go over it entirely. Or at least we'll go over whatever you need to know. Okay, but before that, let's revisit what we did in the last lecture, differentiating and double differentiating a function of a vector x. So it's a multivariate function. And this is a quadratic function. This is q, and so half of summation I, summation j, qij, xi, xj, plus summation pi, xi, which can be represented in vector matrix form as half x transpose qx plus p transpose x. Note that this summation pi, xi is the inner product of p and x, and that can also be represented as x transpose p. Another way of looking at it is p transpose x is a scalar, right? So take the transpose of a scalar. What do you get? X transpose p. Okay, so the derivative or the gradient of this quadratic function is equal to del f of x, which is half of q plus q transpose x plus p. Derivative of the first term is this. The derivative of the second term is p transpose x is p. Now the second term can also be expressed as x transpose p, right? In that case, the derivative will obviously be the same because it's the same scalar quantity. So x transpose p, the derivative of that would still be p. Derivative of p transpose x, which is the same as x transpose p, would be p. Notice that p transpose x, this transpose is dropped here because it has to be a column vector. Okay, this is a column vector. A matrix post multiplied with a column vector is a column vector. Okay, so this is the gradient, and the Hessian is del square f of fx. It's the matrix that we saw in the last lecture, and that is equal to half q plus q transpose. Now, when q is symmetric, then q equals q transpose, in which case this expression reduces to qx plus p, and this expression reduces to del square fx equals q. Del fx is simply qx plus p, and del square fx is q. Now, here's an example. Let's try to differentiate this function, A transpose x, x transpose b. This is a scalar because A is always a column vector. So A transpose is 1 by n, this is n by 1, x transpose is 1 by n, and this is n by 1. All the inner dimensions match, the outer dimensions are 1 and 1, so this is a scalar. What's the derivative of this with respect to x? Okay, we'll look at two methods to solve this problem. First method is using what we just saw in the previous slide. I've dropped the half here, so derivative of x transpose qx equals q plus q transpose x. Okay, now let's try to solve this. Derivative of A transpose x, x transpose b equals derivative of, I group these two together. Note that this is a scalar. A transpose x is a scalar, and this is x transpose b. Well, I wrote b transpose x here, but that's x transpose b, which is the same as b transpose x. Okay, because it's a scalar. And again, this is a scalar, so A transpose x, let me transpose that. I should have written B transpose x here and then done the transpose, sorry about that. But this A transpose x, I can take the transpose of that because it's a scalar, and so this gives me X transpose A B transpose X. Okay, now this is of this form, X transpose times a matrix Q times X. Note that AB transpose is a matrix. It's the outer product of A and B. It's a matrix. And so this takes the place of Q here. So derivative of this is AB transpose plus, that's Q here, and then AB transpose whole transpose X, which is equal to AB transpose plus BA transpose X. Okay? The other way to do it is by applying this formula here. The derivative of the product of two functions, f and g here, is equal to the first function times the derivative of the second plus the second function times the derivative of the first. F del g plus g del f, which you already know. So the gradient of this is del of, again as before, I group them together, A transpose X and B transpose X. And then I applied this. So both of them are scalar functions. So the first function times the derivative of the second, gradient of the second. Remember why I said gradient is because it's a vector, okay? Plus the second function times the gradient of the first. So that's first function A transpose X. What's the gradient of B transpose X? B. B plus B transpose X, gradient of this is A, not A transpose, right? Which now, this A transpose X is a scalar, okay? I want to write X on the the right hand side, and so what I'll do is, this scalar, A transpose X, it's a scalar, so I can put it anywhere, I'll bring it forward. So this is B times A transpose X. I'll do the same thing here. I'll bring this B transpose X forward. So A times B transpose X. Again, I'll remind you that it's only valid exchanging or changing the order of one of the terms is only valid if it's a scalar. Okay, now we have X on the right hand sides of both terms. So now I'll remove the brackets. So I have BA transpose X plus AB transpose X. I'll take X common outside. I get AB transpose X, which is actually the second term here, and plus BA transpose X. AB transpose plus BA transpose X, which is exactly the same result that we obtained the first time. Now let's begin with our review of linear equations. Outline: existence and uniqueness of solutions. We'll do rank of a matrix, condition number of a matrix, and then error bounds. Okay, we'll take up a very simple example. I have, to solve for x and y, I have these pair of equations, two equations in two variables. In vector matrix form, I can write these two equations in this form. So this expression I have to solve. X and y is the variable now, vector variable. And so x, y is this matrix inverse times this vector, correct? And the solution is x is -1 and y is 2. Let's look at it graphically. It's a unique solution. There are no other solutions. Let's look at it graphically. This is twice x plus 3y equals 4, this line here. This is x and this is y. And the second equation here, 5x plus y is negative 3 is this one here. And the solution is where the two lines intersect, right here. That's negative 1 and 2. That's the unique solution because that's the only place where two lines can intersect. Now let's look at this situation here. These two equations, can you see something fishy about this?
They are multiple.
Exactly. Look at the left hand side of the first equation, twice x plus 3y. And the second one is 4x plus 6y. So it's actually 2 times the first equation, right? But on this side, you have 4 and negative 3. You cannot solve this. But let's try to solve it anyway and see what happens. So in vector matrix form, this is what I have. And unfortunately, I cannot invert this. So I cannot obtain this. So xy equals this inverse times 4 negative 3. I cannot invert this. Okay. So in fact, you can see intuitively that we don't have any solution. We don't have any solutions here. Graphically, this is why. This is 2x plus 3y equals 4. Second one is double the first one on this side, right? So the slope is the same, but on this side you have negative 3. So these are the two equations here corresponding to this and this. And obviously they're parallel lines, they have the same slope. The slope is negative 2/3, right? Both of them have the same slope and therefore they're parallel lines. They will never intersect, and so that's why you have no solutions here. Now let's look at this case. I just changed the right hand side. So this, we know that the left hand side, this is something, and this second line, it's twice the first line, the left hand side. But the right hand side, again, I doubled it. Okay, so basically the whole equation, I just multiplied it by 2 here. Okay, and so we again try to solve it. We know that this matrix here cannot be inverted, so we cannot compute the solution. But basically these two are the same, right? So this actually has infinite solutions. It's like one equation and two variables. That's because both these lines are actually the same. Okay. Now, if you want to solve something like this for future reference, this is called an underdetermined system. Okay. And we would like to get the value of x and y. We would like to solve for x and y. X and y is a vector, right? That has the minimum L2 norm. Okay, whenever you have an underdetermined system like this, it's a good idea to find the solution which has the smallest L2 norm, the min norm solution. And that graphically, I haven't showed it here, but if I draw a orthogonal line from here to the origin, then this point here would be the min norm solution. So that would be the solution that we would normally look for. Okay, and we'll look at that when we do optimization. In fact, it's in one of the videos on YouTube. Okay, so this is the situation. Now, in general, we have these are n equations in n variables, x1 through xn. And in matrix form, we can write this as, this is B. I take all the B1, B2 until Bn and make a column vector out of it, B. This is the set of all variables, x1 through xn, is this column vector x. And this is the matrix of all coefficients, a11, a12, all the way to a(n). And I can write all these equations succinctly as ax equals b. Now, that was the matrix form. I rewrote these in matrix form. Now, I can rewrite it in vector form. B and x remain the same. This A, I express A in terms of all its columns. So the first column is A1, A11, A21 until AN1. That's A1. Likewise, the second column, A12, A22 until AN2 would be A2 until this column vector AN, which is A1n through ANN. Okay, so this is my A. So this set of equations can be written as A1, I'm taking this here, this, and this is all my x's, and this is all my b's. And then now this is a block matrix, right? But I can treat them as if they were scalars, as long as I take care of the dimensions and preserve the orders. But here, these are all scalars anyway, so I don't bother about the order. A1 x1 plus A2 times x2 all the way to plus dot dot AN times xn equals b. Okay, so this is what I have. Now here I had a unique solution. Let's examine it using this notation. So A1 is 2, 5, A2 is 3, 1, and this is my B, 4, negative 3. Now the column vectors A1 and A2 are independent. They don't point in the same direction. They are independent. 2, 5 is not some multiple of 3, 1. So the span of A1, A2 is two-dimensional. In other words, I can express any point in two dimensions uniquely in terms of A1 and A2 as the coordinates. I'll use the word coordinates and basis vectors interchangeably. Okay, so these can serve as basis vectors in two dimensions. And any vector can be, in two dimensions, can be expressed uniquely in terms of the basis vectors. Another way of saying this is the rank of this matrix A is 2. A third way of saying this is the matrix can be inverted. It's non-singular. A matrix is non-singular if it can be inverted. Okay. Yet another way of saying that is the determinant of this matrix is non-zero. So these are various ways of saying the same thing. Anyways, so rank of A is 2. It's a full rank matrix. It's a 2 by 2 matrix. It cannot have rank more than 2. It's a full rank matrix. So that's why any two-dimensional point can be uniquely expressed as a linear combination of A1 and A2. Specifically, if this is the vector B, then B can be uniquely expressed as a linear combination of A1 and A2, right? So this is my B, x1 and x2 are its components. So this 4, negative 3 is being uniquely expressed in terms of 2, 5 and 3, 1, the coefficients being x1 and x2. Okay. No solution or infinite solution. Let's look at the other two cases. So these are my two basis vectors now. A1 is 2, 4, A2 is 3, 6. In fact, 2, 4 multiplied by 1.5 and you get 3, 6. So these two are actually pointing in the same direction, right? So one is 1.5 times the other. So you cannot express any two-dimensional point uniquely in terms of A1 and A2. The column vectors A1, A2 are dependent. A2 equals, 1.5 times A1. The span of A1 and A2 is one dimension. You can express 5, 10 in terms of A1 and A2, right? It's equal to A1 plus A2, or it's equal to 5 times A1, or it's equal to 1.67 times A2. That's the vector 5, 10, right? So 5, 10 can be expressed in terms of either A1 or A2, any infinite number of ways. Okay. So now when I have this 4, negative 3, that vector, that's B, right? 4, negative 3, that B cannot be expressed in terms of A1 and A2. Therefore, we have no solutions. Ax equals 4, negative 3 has no solutions because this B does not belong to the span of the column vectors of A. B does not belong to span of A. On the other hand, 4, 8 is in the span of A1 and A2. Well, because 4, 8 equals A1 plus 2/3 of A2. Sorry, this is 2/3 of A2, or it's equal 2 times A1, or it's equal to 1.25 times A2, right? So you can express 4, 8 any way you like in terms of A1 and A2. So B belongs to the span of A. Therefore, you have infinite solutions. Yeah.
In infinite solution, again, A1 and A2 both are multiple of each other. So they are not independent, isn't it?
No, they're not independent.
So the span and the range shouldn't be one.
The span is 1, yeah.
In the infinite solution.
Yeah, infinite solution, yeah, it's one dimensional. It's 1D. It's the same matrix.
Oh, but the B is 4 and 8.
4, negative 3 and 4, 8.
So the B is 4, and in the case of infinite solution, the B is 4 and 8.
Yes.
The span is 1. So how B is belong to span of A?
Because the span is 1.
And
One dimensional.
Okay, B is also 1.
B lies in that same one dimension.
Okay.
Okay.
I got it. Okay, so you also multiple 4 and 8. That's why.
Basically this, if you look at the ratio, this 4 is to 8, it will be the same as this or this.
Okay.
Well, let's extend it to 3 dimensions, and then I'll show you graphically. So we have 3 cases. The determinant of the matrix is non-zero, so we have a unique solution. Now, when the determinant of the matrix is 0, that is, it's not a full rank matrix, it's not a invertible matrix, it's a singular matrix. So this is a singular matrix. Then, if B does not belong to the span of all the column vectors of A, no solutions. If B belongs to the span, then it's infinite solutions. And the span of A1 through AN is the span of the matrix A. The rank of the matrix is the number of dimensions that the matrix spans. Okay, independence, span, and rank, another example. So I take A, B, and C as three vectors in 3 dimensions, and I stack them up together. These are A, B, and C. The rank of this matrix is actually 2. And you can look here, these 3 vectors A, B, and C are not independent because C is actually twice A plus B. So you can have only 2 independent directions. So the span of ABC is 2-dimensional. How about this case? I changed C. Oh, well, everything has changed. A and B and C. And now the rank of the matrix is 3 here. That's because A, B, and C are independent. No vector is a linear combination of the other. So I cannot express C in terms of a linear combination of A and B. I cannot express B as a linear combination of A and C and so on. Okay, and so the span of ABC is 3 dimensions. In this case, for these 3 values of A, B, and C, the rank is 1. And in fact, you can express B uniquely in terms of A. B is negative A and C is thrice A. Or C is twice A minus B, whatever. Okay. So the span of ABC is 1-dimensional. Okay. So rank properties. Rank is the number of linearly independent columns AJ of the matrix A. It's a square matrix, I'm assuming. Rank of A equals rank of A transpose. Now, if it's a general case, M by N matrix, then the rank of this M by N matrix, it's not a square matrix anymore, is less than equal to the minimum of M and N. If I have a 5 by 10 matrix, the rank of that matrix can never exceed 5. Now rank AB, if I have 2 matrices A and B, rank AB is less than equal to the minimum of rank A and rank B. Okay, for instance, A is 8 by 5 and B is 5 by 9. Rank of AB, the product AB, can never exceed 5. Okay. Geometrically, this is what's happening. So I start with a 9-dimensional space, Euclidean space here, which is in 9 dimensions. I take a vector in 9 dimensions, that's x, and then I do this transformation bx. Bx is 5-dimensional because this is 5 by 9. X is 9-dimensional, so bx is 5-dimensional. So from 9 dimensions, I'm compressing to 5 dimensions, bx. And then I multiply this bx with a. abx. I get something that's 8-dimensional. The z here would be 8-dimensional. Okay, but I compressed x to 5 dimensions and then I'm blowing it up to 8 dimensions. No way can I retrieve all the information that I had previously, or 8-dimensional information. From 9 dimensions, when I compress it to 5 dimensions, I'm using the word information very informally, but I'm compressing the amount of information that it has, right? From 9 dimensions to 5 dimensions. A lot of 9-dimensional vectors will map to the same 5-dimensional vector. Okay, so I'm getting rid of information. I cannot restore some of that information back when I multiply the result with A. Okay, so whatever happens, I take all possible values of X in 9 dimensions. And this Z that I'll get, well, in theory, it'll look 8-dimensional, but all those 8-dimensional vectors that I get, infinite number of 8-dimensional vectors Z, because I'm taking all possible infinite number of 9-dimensional vectors X here, and finding out the corresponding Z's. All of these will lie in a 5-dimensional hyperplane in those 8 dimensions. Okay, so let's look at the whole thing graphically. Here's a 3 by 3 matrix A. This is X. I take all the points in this unit sphere, on the surface of this unit sphere, they'll all be unit vectors. And then let those be X, and then AX will be the surface of this 3-dimensional ellipsoid. As a matter of fact, these red, blue, and green lines here, okay, they are the eigenvectors of the matrix A. And if the matrix A is orthogonal, if it's symmetric, then the eigenvectors will be orthogonal, and the directions of the eigenvectors will be preserved when we do AX. Okay, that's something for future reference. You need not know this now. So a 3 by 3 matrix A, we take any unit vector X, it will lie on this surface of this sphere, and AX, the projection of those points, will lie on this ellipsoid, 3-dimensional ellipsoid. If it were 2 dimensions, then it will get compressed to 2 dimensions. If I take all these points, I'll retrieve a 2-dimensional ellipse. Okay, it will never be 3 dimensions if this matrix A is of rank 2. If the rank is 1, then all these points in 3 dimensions here will project onto this. Excuse me, it'll be the same vector. Okay? So, next we move on to condition numbers. The condition number of A, I'll use 2 different notations, this kappa A or cond of A, condition number, is given by the L2 norm of A inverse times the L2 norm of A. Okay? The condition number lies between 1 and infinity. And the lower the condition number, the better is the matrix. The condition number of the identity matrix is 1. That's the lowest you can get. And this is the best possible condition number. If the determinant of A is 0, that is, if it's not full rank or if it's not invertible, singular, then its condition number is taken to be infinite. Note that this expression doesn't hold here, because if the determinant is 0, then you cannot, there is no inverse, right? So you cannot apply this expression here to get the condition number, but by definition, the condition number is infinite if it's a singular matrix. Now, this is bad news. Condition number cannot improve if you scale up the elements of the matrix. Here's a factor alpha. So the condition number of alpha A is the same as the condition number of A, where A is a real number. And the condition number of A equals condition number of A inverse. Why? Because take A inverse, put it here. What's A inverse? Inverse. That's A. And this is A inverse. So the condition number is the same. Okay. Now the condition number of this diagonal matrix is, see, D11, D22, and Dnn. These are the diagonal elements which are non-zero. And all the non-diagonal elements, so the diagonal elements are non-zero, the non-diagonal elements are zero. The condition number of this is maximum of dii divided by minimum of dii. You know what's the determinant of this diagonal matrix? The product of its diagonal elements. Just for reference. So the determinant of this matrix here is of a diagonal matrix is the product of its diagonal elements. What's the inverse of a diagonal matrix? All I have to do is do 1 over D11, 1 over D22, 1 over Dnn, and that will actually be its inverse. And that's why you can reason why we get this ratio here. Now here's an example of a condition number. Okay, let's look at this matrix. A equals this 1, 1, 1 plus epsilon 1. Okay, and let's take two cases here. When epsilon is 10 to the negative 1, it's 0.1. The condition number of A is 42. Now, when I lower epsilon, make it much smaller, 10 to the negative 3, then the condition number is 4002. There's no relationship between this 42 and this 42. It's just coincidence, by the way. Okay. So, why did it increase so much? It becomes worse, right, when you reduce epsilon from 0.1 to 0.001. Why does the condition number deteriorate? Why does it become so bad? That's because when epsilon gets smaller, this matrix A looks more and more like a singular matrix, right? In the limiting case, when epsilon approaches 0, this will be a singular matrix. We know that for a singular matrix, the condition number is infinite, right? And that's why when you keep reducing epsilon, the condition number keeps increasing. It becomes worse and worse, and it will rise to infinite, approach infinity when epsilon approaches 0. Okay, so from visual inspection, you can see clearly that the condition number, how the condition number will change with epsilon. Now, this condition number can actually be deceptive. Okay, let's look at this matrix H. Looks like a perfect matrix, right? It's a nice matrix on the face of it. All these coefficients are very different, and they don't look like one is a ratio of the other or nearly close to it. But what happens when you actually take the condition number? It's so big. So it's not a very good matrix to deal with. So H doesn't look like it's close to singular. Okay, but the condition number is so high. It's a poorly conditioned matrix. Now let's see how condition numbers affect our solutions to linear equations. So we are given this matrix A, this vector B, and we have to solve for x, find x. Now, let's suppose either due to experimental error or whatever, or round off error while storing in the computer, B gets rounded off, or an error in B is introduced. So the B that we have is actually this B hat, which is the real B plus the error delta B. Okay, A is perfect somehow. And now we want to solve for x. Obviously, because of this error in B, we'll get something else. We'll not get the real x. We'll get some x hat, which is the real x, plus some error delta x. Okay. Okay. Likewise, suppose B is known and there's no error in B. Again, due to round off error or experimental error or whatever, we get an error in A. Okay, so A hat is A plus delta A. We don't have the real A, this matrix. What we have instead is a slightly perturbed version of it, A hat. And so we try to solve it. Again, we'll get an error in B. Sorry, in X. X hat is X plus delta X. Correct? So in both cases, we get errors in X. Okay. This is the real solution. If with the real A and the real B, no perturbations, then we would get the real X, real value of X. But due to either the presence of a perturbation delta B or a perturbation delta A in A, we get some other value of X, which is X hat. Okay, so the numerical estimate x hat has an error delta x. Error bounds. So what's the maximum possible error that we can get? First, let's look at when there is an error in B or a perturbation in B. This is in fact what happens. This is the error that we would get in X when we solve it. The error in B is delta B. And we have this upper bound. This delta X, L2 norm, actually any LP norm would work here. This norm of delta X divided by the norm of X. So it's like the length delta X divided by the length of X, right? So look at it as the percentage error or fraction error. So the fraction error in X is less than equal to, so it's upper bounded by the condition number of A. There's no error in A, okay? But it's upper bounded by the condition number of A times the fraction error in delta B, in B. Okay? Let's try to prove it. So this is the true expression, Ax equals B. Now, what we solve numerically is Ax hat equals B hat because we don't have the real value of B. And so we get X hat instead of X. So Ax hat equals B hat. Now, X hat is X plus delta X and B hat is B plus delta B. Whence we get this expression here. I just opened up this parenthesis. Now, since we know that Ax equals B, this Ax and this B will cancel out. So we have A delta X equals delta B. Whence delta X equals A inverse delta B. Now I apply the Cauchy-Schwarz inequality. I take the norms on both sides. So the norm of this delta X is less than equal to the norm of A inverse times the norm of delta B. Okay, so I rewrite this here. Now I have Ax equals B. Apply norms on both sides and take the Cauchy-Schwarz inequality. So norm of A, norm of X is greater than equal to norm of B. Or X is less than equal to B by A. Sorry, X is greater than equal to B over A, norm of B over norm of A, which implies that 1 over X is less than equal to norm of A over norm of B. Are you guys clear with this so far? Now I have these two equations. So I have this and this. And I have the less than equal to on both cases. So I take the left hand sides, multiply them together, take the right hand side and multiply them together. What do I get? This less than equal to still holds. So delta x, norm of delta x divided by norm of x is less than equal to norm of A inverse, norm of A, norm of delta B over norm of B. What is this here? That's the condition number of A. So we established this relationship, and that's we wanted to prove. Okay, this is a very important upper bound, right? So anytime you want to solve simultaneous equations, or actually, for that matter, do some other things, look for the norm of the matrix. When you're dealing with really large matrices, then it's not so easy to find out. You don't want to run a computer for a long time, hours, days, and then find out that you cannot solve it, or you get a lot of errors. So test for the norm first, and you can approximately estimate what the norm would. Sorry, not the norm. The condition first. Test for the condition number of the matrix, and there are ways to estimate what the condition number of a matrix would be. Okay, so that's the upper bound. Now, when there's an error in A, so we get A hat. This is the expression. It's analogous to the previous one. This is the fraction error in A, and the fraction error in X is upper bounded by the condition number of A times the fraction error in A. We begin with the true expression, which is AX equals B. And we solve numerically A hat X hat equals B. The B's are the same, only the A's are different. This is A hat, which is a perturbed version of A. X hat is the perturbed or error added to X. So this is what we have. A hat X hat equals B. What's A hat? A plus delta A. What's X hat? X plus delta X. So this is what we have. And then we open the parentheses on both sides. We do all the multiplications, and this is what we get. Now this delta A, delta X, assuming that delta A and delta X are small, then this is a product of two small quantities, so this will be negligible. Hence, we can simply ignore this fourth term here, delta A times delta X. So what we get is AX plus delta A times X plus A times delta X equals B. I just neglect this term. What's the next step? AX is on this side and B is on this side, right? So, since AX equals B, we know that, we arrive at this little expression. Delta A times X plus A times delta X equals 0. Whence A delta X equals negative delta A times X. Or delta X equals, I can invert A. delta x equals negative A inverse times delta AX. Why didn't I write delta A inverse? Well, to begin with, that won't be the proof. We won't get at the proof, but delta A might be singular. Okay. Hence, now I take the norms on both sides. So, norm of delta x is less than equal to Cauchy-Schwarz inequality, norm of A inverse times the norm of delta A times the norm of x. Then what do? I multiply and divide by A, the norm of A. Okay. So I multiply by the norm of A, this left hand side, the right hand side, the right hand side, and then I divide by norm of A. Okay. Now what does this look like? The condition number. So, and then delta x norm divided by norm of x is less than equal to this quantity here, everything else here. This, in fact, is the condition number. So I arrive at this expression here, which is what we wanted to prove. Okay? I hope you followed all the steps. The only step that was important, that you need to know, be careful about, is the Cauchy-Schwarz inequality. Just a quick review of what we just did. Ax equals b. If it's a non-singular matrix, A is non-singular, then we have a unique solution, x equals A inverse b. If A is singular, the determinant is 0, then if B does not belong to the span of A, no solutions. If B does belong to the span of A, then infinite solutions. Rank of A is the dimensionality of the span of the columns of A. Condition number is given by this expression here, norm of A inverse times the norm of A, and we have just established these two important error bounds. And this is graphically what we also saw. In this case, rank of A is 1. So, all unit vectors x will project onto the same vector Ax. If the rank is 2, then all unit vectors here will project onto this ellipse here in 2 dimensions. It's 2 dimensions because the rank is 2. When the rank is 3, then in general you'll get a 3-dimensional hyperellipsoid. This is also a 3-dimensional hyperellipsoid, a special case, this 3-dimensional sphere. Okay? Are there any questions? Yeah.
So in the error bounds, we actually discussed the 2 cases. In both cases, we keep one matrix or a vector constant. Like in error B,
yes,
we consider that there is no error in A.
Yes.
But is there any case when we may have error in both, maybe B and
Yeah.
A as well?
In both cases, you'll get. I have to think a little bit more, but
There is a possibility that the system may also.
yeah. I understand. So I'm not so sure yet. I have to think about it. But it's probably you have to add up delta with this term and this term together.
Like a superposition, sort of.
Just I'm not going to get into any non-technical terms here. Superposition has a completely different meaning. So this times this ratio plus this ratio. Any other questions? Okay, so we will end this lecture here. Sure, okay. Well, you can do it from your side. Any other questions?